Fenrir is leading another one. Last time was great, so here we go.
Thanks, Erica. Alright, no fluff today. Let us cut straight to what matters. I am Fenrir, your guest host for this episode. Cryptography is the domain where most architects think they understand things better than they do. I am going to be blunt: if you pick the wrong algorithm, use the wrong key length, or mismanage your keys, nothing else you built matters.
That is exactly the right framing. The CISSP exam tests cryptography heavily, not just the names of algorithms, but when to use symmetric versus asymmetric, why key length matters, and what happens when an algorithm is deprecated.
Think of cryptography as a set of mathematical locks. Symmetric encryption is a padlock, same key to lock and unlock. Asymmetric is a mailbox, anyone can put mail in, only you can take it out. Hashing is a fingerprint, you can verify identity, but you cannot reconstruct the original.
Stick around for the key management lifecycle later in this video, where Fenrir shows exactly how brilliant algorithms get defeated by poor key storage. That is the section that trips candidates the most.
8 concepts, Erica and Michael and Bella. No sugarcoating. Let us start with symmetric encryption, the workhorse of bulk data protection.
Starting with Advanced Encryption Standard, the gold standard of symmetric encryption, and one of the most testable algorithms in the CISSP exam.
Here is who is with me today.
I will be keeping an eye on things from over here. Go ahead.
Michael here. This is the kind of topic I could talk about for hours.
Bella here. This one surprised me. I think it will surprise you too.
Great team. Let us get into it.
Symmetric encryption uses the same key to encrypt and decrypt. Advanced Encryption Standard. The Advanced Encryption Standard is NIST's standard since 2001, using 128-bit blocks and key sizes of 128, 192, or 256 bits.
Advanced Encryption Standard with 256-bit keys is the choice for top-level government classification. The algorithm is public, it won a public competition. Its security comes entirely from the key length, exactly as Kirchhoff's principle requires.
3-data encryption standard is the red flag on the exam. It is deprecated and NIST disallowed new uses after 2023. If you see someone recommending 3-data encryption standard for a new system, that is the wrong answer.
Blowfish and Twofish were Advanced Encryption Standard competitors. Twofish was a finalist in the Advanced Encryption Standard competition. Both use variable key lengths and are still considered secure. You may see them in legacy systems or as alternatives in some implementations. But Advanced Encryption Standard is the standard.
The fundamental advantage of symmetric encryption is speed. Advanced Encryption Standard is fast enough to encrypt entire hard drives, bulk data streams, and video content in real time. Asymmetric encryption is orders of magnitude slower, which is why it is never used for bulk data.
The fundamental problem with symmetric encryption is the key distribution problem. If Alice and Bob share an advanced encryption standard key, they had to share it somehow. If that channel was insecure, the key is compromised. This is the exact problem asymmetric cryptography was designed to solve.
For the exam, Advanced Encryption Standard is the current standard, 3-data encryption standard is deprecated, both are symmetric. Speed is the advantage, key distribution is the challenge.
And that key distribution challenge is exactly what asymmetric encryption was invented to solve. Keep that in mind as we go into RSA and Diffie-Hellman.
Asymmetric encryption uses 2 mathematically related keys, a public key anyone can have, and a private key only the owner holds. What one key encrypts, only the other can decrypt. The public key can be published freely. That is the design.
RSA, named for Revest, Shamir, and Adelman, is based on the mathematical difficulty of factoring large integers. If you multiply two large primes, the result is easy to compute. Factoring it back is computationally hard. RSA, key minimum is 2040, 8 bits for current systems.
Elliptic curve cryptography uses the math of points on an elliptic curve rather than integer factorization. The advantage: a 256-bit ECC key provides roughly the same security as a 3072-bit RSA key. Much smaller keys. Much less computation. ECC is preferred for mobile and Internet of Things.
Diffie-Hellman is not an encryption algorithm. It is a key exchange protocol. It allows two parties to establish a shared secret key over an insecure channel without ever transmitting the key itself. That shared secret then seeds a symmetric encryption session.
The key usage rule, and this is a guaranteed exam topic. Encrypt with the recipient's public key to ensure only they can read it. Sign with your own private key so recipients can verify it came from you. Decrypt with your private key. Verify a signature with the signer's public key.
Trap IC on exam questions: signing and encryption are not the same. Signing authenticates, it does not encrypt. Encryption protects confidentiality, it does not authenticate. To get both, you do both operations.
For the exam, Bella and Erica RSA, integer factorization, 2048-bit minimum. ECC, elliptic curve, smaller keys, same strength. Diffie-Hellman, a key exchange only, not encryption. Asymmetric solves key distribution but is too slow for bulk data.
A cryptographic hash function takes any input and produces a fixed length output called a digest. The function is one way. You cannot reconstruct the input from the digest. And it is collision resistant. Finding two inputs that produce the same digest should be computationally infeasible.
Secure hash algorithm, 2 is the family. Secure hash algorithm 256 produces a 256-bit digest and is the current standard for most applications. Secure hash algorithm 256 is used in transport layer security certificates, code signing, and file integrity verification. Know it cold.
Secure hash algorithm 3 is a different algorithm family, based on the Keck-Expunge construction. NIST, standardized secure hash algorithm 3 in 2015 as an alternative, not a replacement, for secure hash algorithm 2. The exam may test whether you know they are separate algorithm families.
MD5 is the cautionary tale, widely used 128-bit digest, but in 2004 researchers demonstrated practical collision attacks. EMD5 is cryptographically broken and must never be proposed for new systems.
HMAC hash-based message authentication code combines a hash function with a secret key. HMAC, secure hash algorithm 256, produces a code that proves both the message content is intact and it came from someone who holds the secret key. That is integrity plus authentication combined in one operation.
The exam trap on hashing alone does not provide authentication. If you hash a message and send the hash, anyone can compute the same hash. HMAC adds the key component that makes it impossible without the secret. Know the difference between a hash and an HMAC.
For the exam, secure hash algorithm 256 is the current standard. Secure hash algorithm 3 is a separate algorithm family. MD5 is broken. HMAC provides integrity and authentication combined. Hashing alone provides only integrity.
A digital signature is a cryptographic operation that provides 3 security services: simultaneously authentication, you know who sent it, integrity, you know it was not modified, and non-repudiation, The sender cannot later deny sending it.
The mechanics: the sender hashes the message with secure hash algorithm 256, then encrypts that hash with their private key. The encrypted hash is the digital signature appended to the message. Anyone with the sender's public key can verify it.
Verification works like this. The recipient receives the message and signature. They hash the message using the same algorithm. They decrypt the signature using the sender's public key to recover the original hash. If the two hashes match, the signature is valid, the message is authentic and unmodified.
The trust problem: how do you know that public key actually belongs to who you think it does? That is where digital certificates come in. A digital certificate is a document that says, "This public key belongs to this entity," and a certificate authority has verified that claim.
X509 is the standard certificate format used in transport layer security, HTTPS, and code signing. An X509 certificate contains the entity's public key, identifying information like domain name or organization name, the CA's signature validating the binding, and an expiration date.
The chain of trust browsers trust a small set of root certificate authorities. The root CA signs intermediate CA certificates. Intermediate CAS sign end entity certificates like your bank's website certificate. If any link in that chain is compromised, the trust collapses, as happened in the DigiNotar breach.
For the exam sign with private key, verify with public key. A certificate binds that public key to an identity. X.LU9 is the format. The CA is the trust anchor.
And digital signatures deliver all three properties simultaneously: authentication, integrity, and non-repudiation. That triple combination is why they are required for legal and regulatory compliance. Key management is where cryptographic systems fail in practice. You can have advanced encryption standard 256, theoretically unbreakable. Then store the key in a plaintext config file on the same server. The algorithm becomes irrelevant.
The lifecycle starts with generation. Keys must be generated using cryptographically secure random number generators with sufficient entropy. A predictable or low entropy key can be brute forced regardless of key length. Generation is step 1, and it must be done right.
Distribution is the step that breaks most systems. Symmetric keys must be exchanged over a secure channel, which usually means using asymmetric encryption or an out-of-band process. Emailing an encryption key in plain text is not a distribution strategy.
Storage requires protecting keys at rest. HSMEMs are the gold standard. Software key stores using encryption are acceptable with proper controls. The principle: the encryption key protecting the data should not be stored in the same place as the data it protects.
Rotation is the most neglected step. Keys used indefinitely accumulate risk: more ciphertext for the attacker, longer exposure if the key is compromised. Rotate on a schedule and immediately on any suspected compromise.
Revocation and destruction close the lifecycle. A compromised key must be revocable through certificate revocation lists, or OCSP for certificates. When a key reaches end of life, it must be securely destroyed, overwritten, or physically destroyed if in hardware. Deletion is not destruction.
For the exam Bella, the key management lifecycle is generation, distribution, storage, use, rotation, revocation, and destruction. Any failure at any step compromises the security of the entire cryptographic system, regardless of algorithm strength.
The birthday attack exploits the birthday paradox in probability. It takes far fewer than expected random inputs to find two that produce the same hash. For a hash with n bits of output, a birthday attack finds a collision with roughly 2 to the power of n over 2 attempts, not 2 to the power of n.
This is why MD5 with a 128 Bit digest is weaker than it looks. The theoretical brute force is 2 to the 128. But a birthday attack only requires 2 to the 64, and practical MD5 collisions are now demonstrated. The birthday problem is why hash sizes matter.
Brute force is the simplest attack. Try every possible key until one works. Advanced encryption standard 250. 6 has 2 to the 250, 6 possible keys. Even with all the computing power on Earth, brute force against advanced encryption standard 250, 6 is not feasible in any human timescale.
Known plaintext attacks give the attacker pairs of plaintext and corresponding ciphertext. They use these pairs to infer something about the key or algorithm. Older ciphers like data encryption standard were vulnerable to known plaintext attacks. Modern ciphers like advanced encryption standard are designed to resist them.
Chosen plaintext attacks go further. The attacker can choose specific plaintexts and obtain their encrypted versions. This gives much more analytical power than simply observing encryption. Many real-world cryptanalysis attacks against historical ciphers used this technique.
Chosen ciphertext attacks flip it. The attacker submits chosen ciphertext and observes the decryption output. This models scenarios where an attacker has access to a decryption oracle. RSA, without proper padding, called raw RSA, is vulnerable to chosen ciphertext attacks.
For the exam, Michael and Fenrir know all 5 attack types and what they target. Birthday attacks target hash collision resistance. Brute force is defeated by key length. Known and chosen plaintext and ciphertext attacks test how much information the algorithm leaks.
Here is your cryptography anchor. Algorithm selection scenarios: advanced encryption standard for symmetric bulk encryption, RSA or ECC for asymmetric operations, Diffie-Hellman for key exchange, secure hash algorithm 256 for hashing.
And whenever you see MD5 proposed for anything security-related, password storage, digital signatures, integrity verification, that is always the wrong answer. MD5 is broken.
The key usage rule is a standalone question type. Sign with your private key so others can verify with your public key. Encrypt with the recipient's public key so only they can decrypt with their private key.
Digital signatures deliver authentication, integrity, and non-repudiation simultaneously. A certificate binds a public key to an identity. XD509 is the format, and the CA provides the trust anchor. The exam tests precision on these relationships.
Key management is where real systems fail. The life cycle is generation, distribution, storage, rotation, revocation, and destruction. Every step is a potential vulnerability. The CISSP expects you to know what fails at each step and what the correct control is.
Drop it in the comments. What is the most common cryptography mistake you have seen in real organizations? Weak algorithms, poor key storage, skipping rotation. Tell us where you see the failures.
Next up is CISSP 3.5, Public Key Infrastructure and Applied Cryptography. Certificate authorities, transport layer security handshakes, SMIM, IP security, and post, quantum cryptography. The DigiNotar breach shows exactly what happens when a CA is compromised. Subscribe and keep the playlist going.
Fenrir signing off. Watch your 6. See you next time. Okay, it is quiz time. Let's find out what's stuck. Think through each question carefully before you answer.
A like and subscribe takes less time than reading this sentence. Do it now and help us reach more learners.
A security architect must encrypt large volumes of database records for storage. Which encryption approach is most appropriate? The correct answer is A. Advanced Encryption Standard 250, 6 Symmetric Encryption, fast, efficient for bulk data, current gold standard.
An organization sends a digitally signed email. Which key did the sender use to create the digital signature, and which key does the recipient use to verify it? The correct answer is D. Sender uses their private key to sign, recipient uses the sender's public key to verify.
An auditor discovers that an application is using MD5 to hash passwords stored in a database. What is the primary security concern? The correct answer is B. MD5 is cryptographically broken. Collision attacks have been demonstrated, making it unsuitable for security.
Good work on the Cryptography Fundamentals quiz. Let me be direct about what we locked in. Advanced Encryption Standard 250, 6 for bulk symmetric encryption, RSA and ECC for asymmetric, Diffie-Hellman for key exchange only, Secure Hash Algorithm 256 for hashing. MD5 is broken, it is never the right answer.
Digital signatures use your private key to sign, and the recipient verifies with your public key. Certificates bind public keys to identities and are signed by certificate authorities. X.509 is the standard format. The key usage rules are testable and precise.
Key management is where real systems fail. Generation, distribution, storage, rotation, revocation, and destruction, every phase matters. The strongest algorithm becomes meaningless if the key is stored in a plaintext config file on the same server it protects.
Next up is CISSP 3.5, Public Key Infrastructure and Applied Cryptography. Certificate authorities, transport layer security handshakes, SMAME-IM, IP security, blockchain, and post-quantum cryptography. The DigiNotar case shows exactly what a CA compromise looks like. Watch that next video now.
Subscribe and keep the playlist rolling. Domain 3 builds on itself, and the public key infrastructure episode connects everything we covered today.
Think in pictures, and the answers follow.
Do not take anything at face value. See you next time.
I have to admit, Fenrir made that look easy. Solid 9 out of 10. Professor Erica signing off.